Hello guys, welcome back. This is the part two of my character display on an old scope module build, and this is the module right here, the second one. I've attached it to the primary module that I showed in my last video. If you guys haven't seen that, you can go and look for part one. Part one is this module right here, which displays a 3x5 dot matrix pattern on this old oscilloscope here. So you can see how that, I've explained everything, and I actually show you the process of how it appears on the scope. Now the second part has to do with this module right here that I just created, and I actually tested and everything else, and tested it, and it works fine. Right now, the way it stands is it can produce numbers on the scope from 0 to 9, and it can produce also 13 out of 26 letters from the alphabet. Unfortunately, you cannot reproduce all the alphabet from the all the letters from the alphabet because the matrix is not big enough. 3x5 is not big enough to display certain letters, normally. Okay, one of the biggest two letters that I can't reproduce is the letter M and the letter W. There's no way you can do that with 3x5. You would need a minimum 5x5. But this module here, you can easily expand it to 5x5, or as a matter of fact, you can expand it to any kind of matrix that you want simply by cascading more sections to the counters, and the R2 ladder, of course. But then if you do that, you're going to have to also extend this these ICs here that will take in the extra bits from the counter. So the circuit just becomes bigger and bigger. Anyways, okay, so to explain this circuit here, what this does is, first of all, the counting system, when it goes to the decoders that I mentioned in my last video, these right here, the output of these decoders, the 7442s, are not exactly what I was looking for. The outputs actually go low in response to binary input. But that's, I didn't want that. I wanted it to start low and then go high. Each pin will go high in response to binary input. So in order to do that, you have to invert it. So two of these chips are inverters right here. Okay, and these inverters, that's exactly what they do. They'll just take the output of the decoders and they just invert it. So they're all high here. So initially they're all high, and obviously here they're all low. So it starts low. And then these two other chips right here, these are AND gates, 7408s. So this circuit does not have anything elegant. Okay, they have TTL chips, standard 7408 NAND gates, and 7404 hex inverters. Just let me get a pen here. And they're wired in such a way as to produce an output on 5 lines that you see right here. The reason that I have 5 lines is because really that's all you need to produce numbers and letters, okay? At the most, you would need 6 out of this combination. But to use 6 outputs from this combination to produce a letter, that's in regards to producing letters that this circuit cannot produce. For example, the letter M and the letter W and the letter Z and X and so on. You would need a bigger matrix, at least 5x5. This will produce a 3x5. So now, what you see here is I've had these pieces of paper here. I'm not sure if you can see it. You probably have to zoom in, but I have them labeled, the outputs from each pin. I have them labeled as, starting from this one, as 1H, 2H, 3H, all the way to 5H. And then this IC, I'm only using 3 gates. The outputs are 1V, 2V, and 3V. And then the AND gates are the special ones. They're designated, the pins output, as, for example, 3H2V, 2H3V, 2H1V, 4H1V, and so on. the reason for this is I'll explain in a minute. But basically, the V stands for vertical, and the H stands for horizontal. So when you're looking at the graph on the dot matrix, what you're basically looking at is a five row high of dots vertically and three dots horizontally. So X position is 3 dots and Y position is 5 dots. So that produces a matrix of 3 by 5. Now, in order to produce a number, you're basically selecting rows and columns. And I'm going to give you an example. The number 1. The number 1, you basically use the center row vertically of the 3 dots. So all you need to connect is this output right here, 2V, because 2V represents the center dots of the matrix. And if you select any output from the hex inverters, you're basically activating all three columns, which are the vertical dots, 1V, 2V, 3V, that represents 3 lines, and vertically, and then you're selecting any dots in 5 rows of horizontal lines. Okay, so 1H up to 5H represents 5 horizontal lines, and 1V to 3V represents 3 vertical lines. So that's why they're labeled V and H. Now, this is kind of backwards though, because the vertical is obviously up and down, but in reality on the scope, it'll scan from left to right, X direction. The horizontal is also backwards. Even though this is X direction, it's actually being displayed on the scope in a Y direction, okay? The reason for that is very simple, is because I've got the horizontal going into the Y-axis right there, and the vertical output, I've got it going to the X-axis. So even though they're coming out correctly out of the chip, they're reversed at the probes, okay? Because it's easier to understand what's going on when you're looking at the scope that way. Now, the way you produce numbers and letters with this is by selecting these outputs and combining them through these diodes right here. These are diodes. You could use an OR gate here, but I elected to use diodes. They do the same thing. Because basically what these things are doing, they're sending out high signals. But if you send a high signal out of, let's say, 1V through a diode, and you connect another line in the same diode, because you only want one output here going to the Z-axis of the scope, you don't want these two outputs to interfere with each other. So the diodes will isolate the signals from each other, and whatever's coming out of each diode will be summed up at this yellow wire, which goes into the potentiometer, and this line right here is actually the Z-axis of the scope. Now, for those of you who don't understand what the Z-axis is of the scope, what that is it's a circuit inside the oscilloscope that is tied into the blanking pulse of the retrace. When the scope is sweeping automatically, there's a blanking pulse in there that retraces the line, and the Z-axis is tied into that blanking system. So what this does, I'm sorry, that's my light going on and off here. I think I have to change the light bulb. But anyways, the Z-axis, what it does is it's tied into the blanking system of the oscilloscope that controls the control grid of the CRT. And by sending a positive pulse through this line, you're increasing the intensity of, increasing the intensity to the grid of the CRT, thereby the dots or the line becomes much brighter, all right? Because you're forcing the CRT to emit harder, or with more electrons, or with the higher voltage and so on. So, you have more electrons and it hits the screen, and it just gives you that extra brightness. So that's what the Z-axis is. But you can use this to show certain characters, displays, or whatever you want by keeping the original sweep of the scope as low as possible and using the z-axis input. Whatever's coming in on this input will be shown on the scope, okay? And I'll give you an example. For example, let me just use one of these lines to activate the z-axis input. I'll just use the line 2V right here. That represents a vertical line, second line. And you don't see anything on the scope. Let me shut this light off right now, just to show you. Sorry about that, something just dropped on my bench. But anyways, this control here will adjust the z-axis intensity. And I added that because if you don't add that, the intensity is just maximum brightness. It's just too bright. So right now there should be a vertical line that is showing basically the number 1 on the scope. If I turn this up, you'll be able to see it. There it is. Okay, that's number 1. Now that's what the z-axis does. You see, if I turn it all the way up, the brightness gets very bright, and then turn it all the way down. So you can adjust the brightness with the z-axis control. All right, or with the potentiometer in series with the z-axis input, sorry. So anyways, okay. I'm just gonna go through the process then of showing you exactly how this thing displays character. So what I've done in part 1 video, you'd have to start from there if you guys are interested to see from the beginning. What I'm creating here is I'm creating a 3x5 dot matrix. Let me expand this so you guys can better see this. All right. Now you see that's 5 dots high. You don't see the 3 dots across because I've only connected the one output line here. Let me pick another number. Well, let me go through the numbers and you guys will see how this thing works. So right now that's number 1. Number 1, I only need the 2V input to the system because, like I said, the 2V will activate all the vertical dots in all the 5 available vertical dot in the vertical direction on the scope, and that will basically make it look like a number 1. Not expanded like that, but if I was to reduce the size like this, okay, it's better. You'll be able to see it better. That's, you know, it looks more like a number 1, especially when you start showing other numbers. Then that definitely will look like a 1. Trust me. But for now, I'm just going to expand it so that you guys can see what's going on. Now, for the number 2, what I need the 1H, 3H, and 5H. Okay, what that will do is that will cause the first row to appear, the third row to appear, and the 5th row to appear. So let's do that right now. So here's 1H. Okay, let me expand that as well. Okay, there's the 3 dots on the bottom. The 3H will do the middle row. There's the middle row. And the 5H will do the top row. Okay, now what's missing here? What's missing is an individual dot, one on this side and one on the front side, right there. Because to write a 2, that's how you would write it, like this. So we have all the rows necessary to display a 2, but we're missing 2 dots, right? Well, the 2 dots cannot be selected by the V's and the H values because they select total rows and total columns. So that's where these the AND gates come into effect here, because now by combining the V value and the H value, you can select one individual dot anywhere in the matrix that you want. So what I want right now is I want the 3rd row and the 4th column up, okay? So that would make it 4H, 3V. So, well, 4H, 3V is right here. So let me connect one line to 4H, 3V, which is right there. Oh, sorry, wrong one. 4H, 3V. Okay, and now you can see that the dot appeared right there. Now I'm missing this dot. I'm missing this dot right here. Now this dot would be the first line, so that's 1V, and the second row up, 2H. So now what I'm looking for is 2H, second row up, and 1V, which is the first vertical row. So 2H1V is the next one. 2H1V is right here. So we'll connect that. And there you go. I have a full number 2. Okay? Now, if I was to reduce this size, like so, and like so, you can still see that it's a number 2. And it looks more like a number 2 because now the dots are closer together, and visually, prospectively, it actually looks like a number 2. But for the sake of clarity, I'm going to expand it because I want you guys to see what's going on here. All right, so that's number 2. So for number 3, what we want is we just want the third row, the top row, the bottom row, and just one dot in the middle here. So let me just, you don't have to remove all of these all the time. You could just move them around. But for this demonstration purpose, I'm just going to remove them all and start over. All right, number 3, we want the top row, still connected one here. Okay, we want the top row. The top row would be 5H. Okay, there's a top row. We want the bottom row, which will be 1H, right there. And we want the third column, which will be 3V. So you can select 3V. You could use any one of these lines. They're not, they're interchangeable, all right? So 3V is right there. So look at that. We almost have a 3. So what are we missing here? We're missing the middle dot, okay, right next to that dot. So that position would be the third row up and the second vertical row from the left. So that would be 3H, 2V. So 3H, 2V is right here. 3H, 2V, and that will create the dot, the missing dot. There you go. And now we have a 3. Okay. Now number 4, we obviously need. We can keep the 3V for number 4. So that's in there. We can also keep. Okay, we can get rid of the 3H2V because we need a row right across here. Well, here, let me start over. That's much easier. All right, so for number 4, sorry, one of my lines came out here. Okay, so for number 4, we need 3V. Did I put that in the right spot? I don't think so. Let me see here. Yeah, okay. So we need 3V. We also need the middle one going across, so that would be 3H, which is here. And then we need the 2 dots on this side, so that would be the first row, so 1V. But we need 4 high and 5 high on the first row. So we need 4H1V, and we need 5H1V. And that will give us the number 4. There you go. All right. Now, number 5 is the next one. Number 5. Again, we're going to have to... Hold on a sec, guys. Just give me 1 sec here because these wires just keep popping off of the system here. Where did this one come from now? Came from... oh, this one here. Okay. All right, so... where were we here? We're number 5. All right, so number 5, we again need 1H, 3H, and 5H. Okay, so for number 5, it's almost the same as number 2, but instead of having the dot on, sorry, this is, what's going on here? Oh, bad controls. Okay, so for number 5, instead of having the dot on this side and this side to make it look like a number 2, we want one on the left top and one on the bottom right. So the left top one would be 4H1V, which is here, 4H1V, and for the bottom we need 2H3V. So 2H3V right there. So that creates number 5, okay? Number 6 now. Number 6, we don't need the top row, so that would be 5H. We can get rid of that. We need 1V complete. And we need the middle one across, which is 3H. And we need the bottom one across, which is 1H. And we already have the dot in the 2H 3V position, so that creates the number 6. Okay, now number 7 is the easiest because you just need the top row and the right side column. So the top row would be 5H, and all these other ones can be removed. And then we need 3V. So 7, you only need 2 of them, okay? Now 8, let me see. 8, we need 5H. 1H, 3H, then we need 1V, and we need the right side, which is 3V, and that creates the number 8. Let me see. Does that look like a number 8? Yeah, if I increase the brightness, it does. There you go. Okay? That's number 8. And then number 9 would be the 3V can stay. Well, let me start again. So I'm going to pull all these off. Okay, now number 9, we would need the 3V, which is the right side. We would need the top row across, which is 5H. And we would need the middle row, which is 3H. And then we would just need the 1 dot right there. 1 dot right there to finish the number 9. So that position is 4H1V. So 4H1V is right here. And there's number 9. Okay? And then, of course, 10 or 0, all you want is you want the top row, right side row, bottom row, and left side row. So the left side row would be, the bottom row would be 1H, the top row would be 5H, the left side would be 1V, and the right side would be 3V, and that creates 0. So we've gone through all the numbers, okay? Now, I do have a sheet here that I wrote all this down. I did it by memory, but, you know, you could see how easy it is, actually. So everything that I just connected is all shown here for these numbers. The first number, these are the outputs that you need to connect to the chip, okay? And now for the letters, you could display all these letters right here: A, C, E, F, H, I, J, L, M, L, O, P, S, T, U. But unfortunately, for a 3x5 matrix that I'm displaying, you cannot display all the letters because they just don't come out looking right. To display the entire 26 letter in the alphabet, you would need an array that is at least either 5x7 or 5x5. Okay. Now, I'm not going to do the letters. It's just going to, you know, make the video longer. But you can see how this thing works. Now, I did it the hard way here. Okay, what you saw is the hard way. This is what I've done is I've chosen individual outputs for each number. Now, you wouldn't leave it like this on the scope either. What you would do is basically reduce it like that. The number's still there, and then just move this to wherever you want it. You know, starting from at the bottom here. Now, if you want to display numbers and characters along the bottom of the scope all the way across, what you need to do is you need to expand on the counters and the decoders and the chips that sum up all the signals. Obviously, the circuit will become bigger, In the case of displaying the other 13 letters that are missing, I actually only need another 3 gates. So that's just one more chip. Yeah, so one more chip, because I have two available here, and I just actually need one more gate. So that, unfortunately, that you need another chip for that. But that will, just adding one more chip will give me the 13 more characters that I can display. So you can see how this thing, the trend of this thing, the way it works, and just by a slight expansion of the circuit, you can literally print on the oscilloscope all the numbers from 0 to 9 and every letter in the alphabet from A to Z. Okay, now there obviously is an easier way to do this other than the way that I did it, because I just did it here for demonstration purposes to show you guys that, my goal was to produce characters on my old scope, and I've done so by using a dot matrix system. So you don't really need, elegant ICs for that. I'm basically using TTLs and just standard gates, so just a little bit of thought has to go into it, and you can make things happen. I mean, I know a lot of guys are using the very common, the very famous LM1881 raster control chip. That will give you your automatic sync signals, horizontal, vertical. You can certainly use that, to adapt to the Z-axis input of the oscilloscope, and you can bring in a video signal from a camera through that as well, and you can use your oscilloscope screen as a video camera. You can do that, but again, there's a circuitry that you have to put together, and you have to understand the LM1881 internal diagram to get everything wired right. Now, using these individual gates are so simple, honest to God. They really are simple, because basically all other logic that we have today is based on these gates. And if you understand these gates, you can understand almost any logic chip there is. And but this is how you do it, okay, using a dot matrix. Now, obviously, it's not perfect, because you're looking at dots that produce numbers and letters. I would prefer actual bars, the way they use in the 7-segment LEDs, but that's a little bit more trickier to produce on the scope. But it can be done, though. I'm not saying it can't be done. But anyways, guys, there you go. Another addition. This is part 2 of the ongoing project for character display on my oscilloscope. And in the next video, I'm going to take all of these outputs, 5 outputs, and I'm going to combine them in another system that will do quick selection of characters. And it's going to be tied into the Z-axis input of the scope. But instead of manipulating these wires the way I've done it here to show you, it's just selecting each one that will scan from 0 to 9, and then possibly some letters and so on. So that system is going to utilize 14 inputs, not 5, because I'm going to use all the available outputs from these chips. So if you add up all the H values, that's 5. The V values are 3, so that's 5 plus 3 is 8. And then these other values, these combo values are 6. So 8 plus 6 is 14 in total. So I need to build a system that will combine all 14 outputs by selection in rows that will select 0 to 9, and then whatever letters A to Z. Okay, so that's going to be part 3, and I will show you that once I get that done and perfected. And but in the meantime, here is part 2, and I am going to show you the diagram for this. Just give me a sec here while I search. Okay, here is the diagram for part 2. Now, you can see here, these are the decoders that comes from the first circuit that I did the video on, from these decoders. Okay, so That's what this is showing here. These two chips are these decoders. So like I mentioned, the decoders outputs are high and they will go low to select whatever binary data you're triggering them with, but that's not good enough in my case. I needed them to be all low and high, so I had to use inverters, like I said, which are these. And then from the inverters, they just go straight out to your 1H and 1H, 5H to 1V, 2V, 3 outputs. And then to get the combination to select individual dots in the matrix, you have to combine a couple of outputs through AND gates, okay? And that'll give you your combination. For example, this one here will tie in the 2H output with the 1V output, which is this one here. So this output will only give you a signal when the 1V output is active and the 2H output is active at the same time. That's what these values mean, okay? So the next one is 2H3V, 3H2V, 4H1V, 4H3V, and 5H1V. I know it sounds complicated, but it really isn't. The V stands for vertical, the H stands for horizontal. All right, and that's how simple that means. So that is. So what that means is it's 2 rows in the horizontal direction, which is connected to the Y axis input of the scope. So that's actually going 2 rows high. Okay, it's reverse of what it says, but the actual circuit is actually producing 5 pulses horizontally and 3 pulses vertically, but I've reversed it because I wanted 3 across and 5 up instead of 5 across and 3 up, okay? So it's kind of confusing, but that's the way it worked out when I designed it, so I left it that way. But anyways, guys, you see how simple this part 2 circuit is. It's really nothing. It's just a bunch of inverters and AND gates, and you wire them like this, and that's it, and you have your outputs. Now, in total, like I said, you have 14 outputs right here. Now it's just a matter of combining all of these into another matrix that will give you one selection for each number that you're trying to recreate on the scope. But as you can see, my goal has been accomplished as far as this point, all right, because I did say I wanted to create characters on the screen. I started with a 3x5 matrix. I ended up displaying numbers on the screen and alphabets. I have not shown you the alphabets, but I guarantee you it's there. And in the next video, part 3, I will be showing you how to combine all of this to do a quick selection of the number system that will show on the scope immediately. All right. Now the output, like I said, you should use a trim pod or a potentiometer, like I'm doing here, because the Z-axis input on these old scopes, well, in my scope anyways, it doesn't have any adjustment for that. Okay, it's just whatever signal's coming in will give you full intensity, maxed out. So you have to have some kind of control there because you want to be able to control the intensity. All right. And again, for those guys who were not sure about what the Z-axis input did, that's all it does. It just controls the intensity of the CRT grid control. That's it. And the Z-axis is actually part of the blanking retrace circuit of the oscilloscope. All right. So there you go, guys. And continuing on this project, and I hope that you guys like this one as well. If you do, please give me a thumbs up. Hit the notification bell. I really haven't found where that is still, even to this day. So, but I'll say it anyways because everybody else says it. And please do not forget to subscribe. I'll keep this going for you. And you know, I just love bringing you this kind of stuff. I hope it helps people to understand, you guys to understand the simplicity of using old style logic gates. This is from a gate level. It's not, it has nothing to do with having an IC and trying to understand what the IC does. You know, the new technology today has so much compacted circuitry inside of it. It literally makes it impossible to understand nowadays. But these logic gates are so simple to understand and so easy to wire. And the only problem with them that I found is in order to produce something, you have to have a lot of them. Okay, but really, if you have the available components to do it and other parts to put it together, why not? You know, like what are you holding on to them for? Do you know what I mean? It doesn't make sense. You might as well use them and use them in the best way you know how. This system right here, I'm really loving this. I hope you guys love it as much as I do, because I am basically trying to turn my old oscilloscope into one that can also display characters according to signal levels that are coming in. And I'm going to continue this until I get to that point, believe me. And at each phase, I will make the diagram and the circuit available to you to show you how it functions, and then I'll show you the diagram for it as well, because I would love you guys to put something like this together too, and let me know through the comments or any remarks you want to make. Let me know like any modifications that you made, or what other uses have you used it for, because this is very interesting to me. I hope it is to you too. And one way of staying in touch with each other and to keep following the system is through subscription. And that's why I keep reminding everybody, don't forget to subscribe. And guys, thank you so much for watching. I hope you've enjoyed this as much as I loved bringing it to you. And I hope to see you on the next one. Take care. Have a good day. Until next time, goodbye, guys. Thank you.